Hey, chemistry people. All right. So this is going to be an overview of gases. So we're rounding out the year here. The last unit is gas laws, and I just want to make a couple of quick videos that are going to go over the basics of what you guys need to know. So first of all, yes, we're talking about gases. You know, the solid, liquid, and gases. Okay. So today we're not talking about liquid. If you look at the box right here, this diagram is to remind you that gases take the shape of their container, okay? Gases are a phase or a state of matter, however you want to look at that, a phase of matter, state of matter. They do not have a definite shape. In other words, whatever you put them in, they will take that particular shape. Behind me, for example, we have these balloons that are filled with helium, but they're pretty full at the moment. The longer they sit there, as you know, they're going to be less and less full. Gases have no definite shape or volume. So in this case, those are round balloons, but the other ones that are going to go with it are, you know, your traditional shape balloons. So it'll take whatever shape that you put it in. And if you put too much in there and there's not enough space, it will pop. Gases have high kinetic energy. And if you look at your diagram up here in the corner, if you follow my mouse, you'll see that there is a solid down here on the bottom with liquids in the middle, which are still taking the shape of their container. And then over here on this side, you have gases, which will take the shape of their container regardless of how big it is. You know, liquids, when you pour a liquid, if I were to, for example, pour my coffee cup out, that would be a poor choice because, as you guys know, it would just take the shape of my desk, which I would be upset about. Okay, they're randomly organized, though, in a gas situation. So they're going to expand up and out and take the shape of whatever it is that's going on. The properties of gases, they're a state of matter. Matter is anything that has mass takes up space. You guys remember that? It's that thing we've been pounding in your heads. And you guys have been regurgitating to us for the last, 15 years of your educational career at this point. An example of a gas is oxygen. Most of the nonmetals on the periodic table, so everybody to the right-hand side, almost everybody to the right-hand side of the stair step, metalloids, most of them are gases. There's a couple of exceptions. And then, of course, hydrogen is all the way over on the left-hand side in group 1, also a gas. Most gases are colorless, odorless, and tasteless. Kind of like water. Water's a liquid. There's a lot of things, though, that look like water, but they're just not water. Gases are the same way. Gases are usually colorless, they're usually odorless, they're usually tasteless. There's some exceptions to this, so I say that to remind you that just because it's clear, colorless, odorless, etc., doesn't mean that it's safe. Iodine is an example that's different. It's a purple gas, mustard gas. We used to use that in the military. It apparently has a smell like onions or garlic. I've not ever had the privilege of smelling that. Another one is chlorine gas. It's a green gas. And highly poisonous, toxic to us. Okay, the next one is methane, which, yes, those are flatulence, poops. They have a stinky odor, okay? Propane has a definite taste if you cook with propane. I'm not a grill snob. In fact, I'm just kind of learning to grill. I'm pretty terrible at it, if you want to know the truth. But I use a gas grill because I don't want to sit out there and wait on the charcoal briquettes to get to the right color or temperature or whatever, because, you know, the color of the briquettes apparently tells you the temperature. You know? So I cook with propane. That means I have one of those big tanks underneath there, kind of like the tank of helium that's sitting beside me, except I would not be filling up balloons with propane because that would be dangerous, right? Some gases are flammable, for example, like propane. The Hindenburg blimp exploded because it was filled with H2, which you guys know, just a blast from the past, H2 is hydrogen gas. Why does it say H2 there? It's a diatomic molecule. Remember, your 7 starts on number 7, goes down, diatomic molecule. Helium, however, is not flammable. Hydrogen is extraordinarily flammable. So is oxygen. That's why when you walk in the building, when we used to walk in the building, or some other buildings for that matter, there's a sign that says oxygen is in use, and that lets you know that there's a substance on campus or in your vicinity that is flammable. Some gases are more dense than others. For example, a balloon filled with carbon dioxide, in other words, whatever I exhale and blow up, is going to just sit there. and a balloon filled up with helium is going to float away. So when you fill up a balloon with carbon dioxide, which is, to say that you blow one up out of your lungs, like, with your mouth, or if you fill up a balloon with helium, I'm pretty sure you guys would expect different things to happen. However, I have two balloons here. One is filled up with carbon dioxide, excuse me, did I say hydrogen? That would be bad. One of these is filled up with carbon dioxide, and one of these is filled up with helium. And when I let go of them, one of them is going to fall to the ground, and one of them is going to not fall to the ground, and I'm going to hold on to it with a string because if it goes to my ceilings, I won't be able to get it back. So the reason that one of these is going to fall and the other's not is density. It's the density of the gas. And so if I let go of this guy, he falls. And if I let go of that guy, he goes as high as he can. So when I go and put balloons on people's mailboxes, I want them to float. So I had to rinse a helium tank in order to do that. I can't just grab helium out of the air. But the basic reason is it's less dense. Now, I also would encourage you, go back and look at your periodic table. Where exactly is the helium? Oh, that's funny. It's at the top. Okay. So moving on. If we're looking at this, gas particles can be compressed. In other words, forced close together, such as this balloon right here being like this. If I pushed on it hard enough, what would it do? Pop. Or if I had put too much helium in it, it would also pop, right? Okay, so if you're looking at these pictures right here, this is designed to show you a pump. And these are the same amount of molecules on the left as what you have on the right, okay? So over here, because there's a closure, a lid, or whatever you want to call it, at the top of this apparatus, this container that's at the very top right now, it's allowing these gas particles to spread out and take up as much space as they want. Down here, though, it has been pushed, and so these particles are being compressed together. Think about this like a pump where you're pumping up your bike tires or things like that. You're pushing it into another direction. Okay, the kinetic molecular theory, you guys are not going to have test questions on this, but I do think you need to know what it is. It's a theory that describes the ideal behavior of gases, okay? Ideal means in an ideal world. Now, we all live in the real world, as I'm sure we know at this point, but this is not a perfect world. Things are not perfect around us. Yes, what goes up generally comes down, but, if that's the case, how do birds fly and how do airplanes fly? So not everything that goes up comes down. We can kind of manipulate and control things. And so that's what the kinetic molecular theory is that these gas laws that you guys are about to learn, because this is kind of step one here, the gas laws that you guys are about to learn, they're not necessarily how things behave in the real world. They're how things would behave in the lab world, in the perfect world, okay? So the KMT describes basically 5 things. 1, gas particles do not attract or repel each other. They're not magnets. They're not like, ooh, I see a positive, ooh, I see a negative. They don't work that way. They don't have charges. Remember, go back to your covalent and ionic bonding. Remember, sodium loves some chlorine because sodium's got a +1 charge and chlorine has a -1 charge. And +1 and -1 are like, hey, let's balance it out, right? Okay, well, that's not the way for gases. Remember that they don't have a charge. Okay, that's the reason you have diatomic molecules. Okay, gas particles, the second part of the KMT, kinetic molecular theory, gas particles are small compared to the distance that separates them. They're teeny tiny little guys. Number 3, gas particles are always moving. They're always moving in a random, constant, continuous motion. They move in straight lines until they collide with one another in the container, and then they change direction. This goes back to what you guys would have learned in 8th grade. An object continues in its motion unless it's acted on by another force. And that's how the gases work. They're a state of matter, right? Different, same as everything else. Number 4, gases collide in elastic collisions. What's elastic do? If you have something that's elastic, what's it going to do? It's going to, snap back on you, right? Stick is like stretchy, right? Elastic, stretch, but then it goes back to the way that it was, okay? So gases collide in an elastic collision, which means that no kinetic energy is lost. It's not like, bam, this one hit and it transfers to another. When gas molecule A hits B, A transfers all of its kinetic energy to B, and B is in motion. So in other words, it's one comes in here. Let's say that this guy's floating here. Another one comes in and hits it, bam, and then that one moves. So I think of it more like the perfect game of pool, You hit that ball really nice, and the ball that you were using in between just kind of stays right there. Sorry, my dog is growling. Do you hear him? He's not a big fan of the balloons today. He sounds a little scary, but he's not. He's scared of a balloon. Okay. And the fifth thing that's up here is that all gases have the same amount of kinetic energy if they're at the same temperature. Remember, temperature is a measure of kinetic energy. Okay, remember, all these things go together. Potential energy, kinetic energy. Potential as you have it, kinetic as you're using it. Temperature is just a measure of that kinetic energy. So if I take your temperature, which has been going on a lot lately, hasn't it? People have been taking everybody's temperature. If you take it on your forehead, what you're really doing is you're really measuring the kinetic energy of the molecules in your body. And so when you're measuring that, So when you're measuring that, that's your kinetic energy. All gases have the same kinetic energy if they're at the same temperature. If they're not, that's a game changer. Okay, so let's also remember that when we're talking about real gases, they're real. They don't behave according to the kinetic molecular theory. They behave according to, real life, like the rest of us. Things should go a certain way, but they actually go another way. Okay? So in order to understand how gases behave, though, we have to look at them according to the 5 tenets of the kinetic, tenets means parts, of the kinetic molecular theory. That's how we study them. We study things in lab, ideal conditions, and then we explain how they would really operate in the real world. Okay, that's pretty much it.